Okay, folks, hello. It's Unit 3, Day 5. Today's our last day of the unit in a video form. So after this, we're getting close to our test. We'll reevaluate and decide if we liked the videos or we didn't. We're going to review a couple of things and learn just one new thing. Quadratic systems are when you have two equations given to you together and you have to solve for both x and y. You learned this in Algebra 1 and you probably also reviewed it in geometry last year. But the smartboard's acting up a little bit, so I don't know, I'm going to do my best here. But this is example 1, where you have y equals this parabola, y equals x plus 1, this line. And right now, if you chose to subtract them down, the y's, of course, would drop out. That would be a method of elimination. So if you wanted to subtract these and work down, y minus y would give you 0. I've got x squared, and then I've got a negative 2x minus another x. I get 1 minus 1, which makes the 1's drop out, and of course now I would factor this with the GCF of x. Set each of those pieces to 0. Those give me the 2 x's, and then you'll go back and plug in. You can go back to either one, whichever one looks better to you, to substitute and get the y. So y would be 1 here, y would be 4. So my answers are 0, 1, and 3, 4. That's using elimination. Typically for a parabola and a line, those students would have used substitution instead. Substitution just says if y equals all this stuff, right down there where you see the y, you can substitute all that stuff in for it. So essentially you just set the two things equal to each other. And then again, what happens with this stuff? It subtracts over this way. Everything moves over to one side. So you can see that we are going to end up getting the same equation. The 1's drop out, and now I am set to 0. And it would finish the same way, of course, as the other one did. We would solve for x, solve for y. So those are the two methods, substitution or elimination. Our next example, one other quick thing. Those, of course, are algebraic solutions, right? These are the two options for algebraically. Graphically, we could have graphed the parabola, graphed the line, and found the points where they intersected or crossed. And of course, we would use our graphing calculator to get a t-chart. We would graph it carefully and find points of intersection. In this example, if we try to do it graphically, we're going to see a parabola and a line, but they are not going to have points of intersection. So when you learned that in 9th grade, you probably wrote no solution or something like that. There is a solution. It, of course, is imaginary, so there's no real solution. So this is I almost want to say it's almost like an honors topic. We'll cover it. I think you should see it, but I wouldn't be too worried about these really tricky ones because this is probably as extreme as this type of example gets. Again, if y equals this stuff, right up here where you see the y, you can substitute that stuff in. So I'm going to solve this with substitution, which means 2x minus 5 equals the x squared minus 2x plus 1. And then I'm going to move everything over to one side. Move that over there, add the 5 over there, and set to 0. And now typically you would factor and say, oh, what multiplies to 7 and gets me to 4? Nothing multiplies to 4 and gets you to 7. So now you have options to solve a quadratic that was not factorable before. I'm going to choose to complete the square. You may also choose the quadratic formula, which is the ABC, the big formula, but I typically complete the square whenever there's a 1 here and this is an even number. So what I'm going to do is I'm just going to move those to this side, and I'm going to move the 7 to that side and kind of rewrite it. So it's typical that the quadratic's on the left and the number's on the right. Remember, the idea was cut the middle number in half and then square it. Half of 4 is 2, 2 squared is 4, and that is the number that we're going to add to both sides. We'll factor this side, which is x minus 2 times x minus 2. On this side, we'll get negative 3. Now I'm going to just switch over here to the top. I get x minus 2 quantity squared equals negative 3. And now we're going to square root both sides. The only thing I'll be able to do with this is bring out an I. So now I'm at plus minus I radical 3. Over here, x minus 2. I will move the 2 over with addition. This is my answer. So you can do that, or you could have split it into the 2 and made the 2 x's if you like. But remember, these are both x values. We also need to get corresponding y values. So I got 2 plus I radical 3, and I got 2 minus I rad 3. You're going to substitute back up above into the x spot, and it doesn't matter which one you go to, whichever equation looks easier. So I'm going to go to y equals 2x minus 5. And I have to put that in for x. So it's going to be 2 times 2 plus I rad 3 minus 5. And then this other one's going to be 2 minus I rad 3 minus 5. So basically I subbed each of those in for x. We'll distribute and kind of reduce this a little bit to get our y. So I think we get 4 plus 2 I rad 3 minus 5. That 4 and the negative 5 will combine and make negative 1 plus 2 I rad 3. Same thing over here, I'll distribute. I end up getting y equals 4 minus 2 I rad 3 minus 5. 4 minus 5, again, ends up being negative 1 minus 2 I rad 3. So you'll notice that, of course, the x values were both conjugates. The y values also will always be conjugates. My final answer will be this x gave me this y, and then this x yielded this y, and those are your solutions. There is no way to solve this graphically. You have to solve algebraically. You can begin the same process, either substitution or elimination, but once you move it all over and set to 0, if the quadratic does not factor, now you'll have the options of doing the complete the square or the quadratic formula. But if there's imaginary solution, i's, you cannot solve it graphically. Algebraic is the only way to go. Okay, that was one big idea, just a review of systems. Big idea number 2 is just to review circles again. We've spent a little bit of time talking about circles in the complete the square portion. So I just want to show you these 2 examples that ask you to write the equation of a circle with a certain center that passes through a certain point. You did do this last year in geometry, and you typically would have used the distance formula to find the radius. But I want to show you a different option. So here at this point, if you remember your equation of a circle, it's x minus h squared plus y minus k squared equals r squared, where the h and the k stand for the center point. So when they tell you the center is negative 3, positive 1, negative 3 is going in for h, 1 is going in for k, and again, it's got that minus already in the problem. So it would really look kind of like that. And here, of course, that minus and negative changes that and makes it look positive. So to here should be okay. I have to scooch that down a little bit. So let's just pull this all the way down and go back up. Oops. Oh, it's not going to cooperate too well, is it? There we go. All right, so the issue is normally we're looking for r and you would do the distance formula. The distance formula is still an option for you. So if you like the distance formula and you remember it and you can work with it well, go ahead and use that. But another option to give you just a different look is to remember that if this point is on the circle, this equation is passing through that point, it has to hold true in this equation. Not for h and k, but for what? If it's an ordered pair, for x and y. So I can take that point that's on the edge of the circle and substitute it in for x and y, and then I will be able to solve for r. So I'm going to get 0 plus 3 plus negative 1 minus 1. This can go into the calculator in one jumbo step if you want, otherwise you have to do it by hand. 0 plus 3 is 3, 3 squared is 9. Negative 1 minus 1 more is negative 2, negative 2 squared is 4. My radius squared is going to be 13. And remember, you need in the equation radius squared. There's no point in finding the radius because this whole equation calls for r squared. So you're going to go back up to this point right here, and instead of r squared, just put in 13. And this is your final answer. You may have learned that last year when you were in geometry. It's another option to avoid the distance formula. So the center goes in for HK, and the point that's on the circle goes in for X and Y. And then you just throw all that in the calculator to get the R squared. Let's try one more example. Remember, feel free to back up the video or to pause if I'm going a little quick for you. Here we've got, write the equation of a circle with a center here that passes through that point. I would start with this kind of generic circle equation where H and K refer to the center points. So I'm going to have X plus 5 and Y minus 2. So this point that was the center just goes in for H and K. And now I'm trying to find R squared. This will be my finished product if I knew what R squared was. So now I'm going to put this negative 8 in for X and the 4 in for Y into this equation. So it's negative 8 plus 5, quantity squared, 4 minus 2, quantity squared equals R squared, and we're solving for R squared. So again, negative 8 plus 5 will be negative 3. Negative 3 squared is 9. 4 minus 2 is 2. 2 squared is 4. Oh, wow. Okay, so this is like a real super unfortunate coincidence that it turned out to be 13 again. That just worked out that way. It certainly isn't always 13. It just is whatever you get. That just kind of happened twice. So now we go back up to this line and get rid of that R squared and just put in 13. And this, again, is your final answer right here. I'm going to box it in yellow. This is your equation of a circle with the correct center that would pass through that point. All right, that was idea 2. Big idea number 3, our last one, is talking about parabolas in a new form, this thing called vertex form. We're used to standard form, which is the ax squared plus bx plus c. And now you're going to see the parabola in this new way, as a quantity squared with a number tacked on the end. This is kind of the generic where HK is the vertex and x equals h is the axis of symmetry. So I know this, maybe doesn't make a lot of sense, but let's do a couple examples and then you'll kind of see what I'm talking about. So let's do the old way versus the new way. If you had seen this last year, and you may have seen this last year, you probably would have FOILed this out. So you would have written x minus 3 times x minus 3 and worked that all out. We end up with x squared minus 6x plus 9 plus 2. So my final answer here is x squared minus 6x plus 11. And now my question for you is, do you remember how to find the axis of symmetry? It was a little tiny formula. This is again from Algebra 1. It was x is equal to negative b over 2a. Well, guess what? Does that formula look like another formula we've already studied this unit? It's the song, right? X is equal to negative b all over 2a. It's that portion of the quadratic without the plus or minus the square root. This, again, is your formula for the axis of symmetry. So you learned the formula before, but you had no context for it being connected to the quadratic formula, no song about it, no anything. Now it should possibly make a little more sense and be a little bit easier to memorize. So again, using this quadratic right here, we're just going to list A is 1, B is negative 6, C is 11, and we're going to plug into this. So it's x is equal to negative 6 over 2 times 1. This is 6 over 2. My x is 3. That's my axis of symmetry. And it's also the x portion of the vertex or turning point. So if the x is 3, I'm going to plug 3 in here and substitute and get the corresponding y. So now I go back to this equation, put the 3 in and get the y. This, by the way, is how you would do this if you didn't have a graphing calculator. 9 minus 18 plus 11. That and that make negative 9 plus 11. I think the answer here is 2. So my whole point here is that 3, 2, this x, this y, is the vertex or turning point of that parabola. Now this is, again, how you do it longhand. I'm guessing that many of you never saw this before or never had to do it longhand. You probably just went to the graphing calculator, typed it in, found the t-chart, and then found the middle value that has not a match. Like there was like all the y's had a match except the one in the middle of the chart was the turning point or vertex. This is how you do it by hand. Your teacher probably showed you maybe once and then you kind of went to the graphing calculator. all that work. Now, again, that you're fancy trig students, when you look at this, you don't have to do any of that work. You can grab the turning point right off of this. My turning point is 3, 2. The y coordinate is exactly the same, and the x coordinate is that number with a flip a sign. So it's positive 3, positive 2. Do you remember, just like in the equation of a circle, that x minus h part, that the sign always flipped on that, but it doesn't flip on that, and that's just your vertex. So I know the vertex, or turning point, right away by looking at the equation. I don't need to do this portion out where you FOIL the whole thing out. That's how you would have done it. Now you can do it like this, a little bit briefer way. All right, a couple more quick things and we're almost finished. You should be able to predict what a parabola is going to look like based on the equation. So this, again, luckily you have a graphing calculator right there so you can kind of see what's going on. But as the A meaning the number that's in front of the x squared gets bigger and bigger and bigger, the parabola will get more and more narrow. So if you type this in, this x squared just looks normal. 4x squared, it's going to be a little bit like that. 10x squared, it's going to be super up and down like that. Closer and closer to the y-axis. And then the reverse is also true. As the A gets smaller, the parabola gets wider. And think about that. Why is this? This is getting closer and closer to what? To 0. If it's 0, there's no x squared, and then guess what? You're not going to have a parabola anymore. You're going to have a line, so it flattens out. As the other values move, the C, the number on the end, the C moving is the up-down. So this, as this number goes to +2, that means the entire parabola shifts up to +2. Or here, the whole parabola is going to shift up to +4. So you're just going to have the generic x squared. Here you'd have it up at 2. Here you'd, oh geez, what happened there? Here you'd have it up here at 4. So this number is the up-down move, and it does exactly what it says. If it says +4, it goes up. Here I've just changed it and made it a negative, which makes it the frown. Remember, it does not matter if it's a happy smiley face or frown kind of parabola, but if it's -1, that means the entire thing is going to shift down to -1 on the y-axis. Here the whole thing is going to shift down to -5 on the y-axis. This is your up-down move, and it's exactly what it looks like. Think of even when you had y equals mx plus b, that number on the end was always the y-intercept. And then the last thing is the left-right shift. As this number inside the parenthesis changes, that's your left-right move. And that does the opposite of what it looks like. So if you have y equals x squared, it's just generic parabola. But when you have this x plus 5, it's actually going to shift the whole parabola over like this to -5. And this one, even though it looks like -3, is actually going to move over here to be +3. So the number that is in the parenthesis is the left-right shift, and it does the opposite of what it looks like it's going to do. The number that's tacked on the end is the up-down shift, but it does exactly what it looks like, and the number here in front determines how wide or how narrow. Yeah, that is all that I have for you for today. The good news on all this business about how the graphs shift is that you do have the graphing calculator. You can type it in and see that it's over there at +3. However, you should have a good sense of that, how those things move, because all the other functions and graphs that we are going to study this year, including the radical, the absolute value, a lot of ones from the next unit, follow that same pattern. The left-right shift, the up-down shift, and then how wide or how narrow. So the idea is that now that we're in trig, we understand the parabola and how it's moving and what's going on. Remember, we talked about the discriminant and roots and how things meet. Last time we talked about sum and product and how those numbers are determined in the equation. And here they want to make sure that you're not just a robot typing it into the calculator and looking, but that you actually have some understanding of what the parabola should look like. When you look at it, you should have an idea. So actually, let's just throw one more on for the heck of it. So if I give you something like this, you should have an idea of where it's going to fall on the graph and what it's going to look like. Is it a smiley face or a frown? It is the smile kind of parabola. This is our left-right shift, and it's the opposite of what it looks like. So it looks like -7. You'd think it moved this way, but instead it moves over here to +7. and then up 5. So basically, and then 2, kind of it's gonna look something like this. And I know that with no calculator, that this is up to 5, this is over to the right 7, and then this determines it's gonna be a little more narrow than a traditional one. But again, you've got the calculator as a backup at the beginning. So that's it for today. Please get into AA anytime if you have any questions. I don't have any extra practice for you, but we will practice right away when you come into class. And then we're at review and test, so the unit is almost finished. Thanks. Have a great afternoon, guys. We'll see you tomorrow.